1942. The air in a New York high school classroom is thick with the scent of chalk dust and floor polish, a familiar aroma of institutional learning. Outside, the world is at war, a global conflagration demanding innovation, intelligence, and grit. Inside, a young Joan Feynman, her mind already alight with the cosmic questions that danced in the night sky, raises her hand. She isn't asking about algebra or American history. She is reaching for the universe. She confides in a professor, a man entrusted with shaping young minds, about her dream of becoming a scientist, of unraveling the mysteries of physics. He looks at her, perhaps not with malice, but with the profound, unthinking certainty of his era. He leans back, the authority of his position amplifying every syllable. Girls can't do math, he states, and physics is too hard for them. This was not a suggestion. It was a verdict. It wasn't one man's opinion. It was the echo of a deeply entrenched societal belief, a chorus of voices that had, for centuries, defined the boundaries of a woman's intellect. In the 1940s, a woman's ambition was meant to be domestic, her contributions aimed at the home front, not the cosmic frontier. The paradox of the era was staggering. While posters of Rosie the Riveter celebrated women's competence in factories, building the very machines of war, the intellectual citadels of science remained fiercely guarded male domains. A woman could assemble a bomber, but she was not supposed to calculate its trajectory through the heavens. The message was clear: your hands are welcome, but your mind is not. This professor's words were not just discouraging, they were a systemic pronouncement. A gate slammed shut and bolted before she had even taken a step toward the threshold of her dreams. But a mind like Joan Feynman's could not be so easily contained. Her fascination was not with the terrestrial, but with the ethereal, specifically the Aurora borealis. At that time, the aurora was a phenomenon steeped more in folklore than in hard physics. Scientists knew it was connected to the sun, but the precise mechanism was a profound mystery. Early pioneers like Christian Birkeland had proposed that electrons from the sun were guided by the Earth's magnetic field into the upper atmosphere, but his theories were largely dismissed for decades. The field of space physics didn't truly exist yet. The aurora was a beautiful, chaotic puzzle, a spectacle of light that defied the neat equations found in textbooks. It was precisely this kind of untamed, magnificent problem that captivated Joan. The vibrant greens, the shimmering purples, the curtains of light that rippled across the polar skies, they weren't just a pretty display. To her, they were evidence of immense, invisible forces at play, a cosmic conversation between the Earth and its star that she desperately wanted to understand. Her own family provided a complex backdrop to this institutional resistance. Her older brother, Richard Feynman, was already on a trajectory toward becoming one of the most famous physicists of the 20th century. It was he who had first sparked her scientific curiosity, paying her to be his lab assistant and offering her a book on astronomy that opened her world. This created a strange duality in her life. At home, a nascent intellectual partnership. At school, a wall of dismissiveness. The support from her brother was a crucial lifeline, yet it also cast a long shadow, one that would follow her for much of her career. She was not just a scientist, she was a scientist's sister, a label that both opened some doors and subtly questioned her own independent merit. The world was prepared to accept one genius from the Feynman family, but was it prepared for two? Especially when the second was a woman daring to enter the same field. The professor's casual dismissal, therefore, wasn't just an insult. It was a challenge to her very identity and a reflection of a world that saw her potential only in relation to the men around her. It was a world that had not yet learned that brilliance is not a finite resource, nor is it confined by gender. The Aurora continued to call to her, a silent, luminous rebuttal to the voices that told her to turn away. How could a mind so clearly drawn to the universe's most complex and beautiful puzzles be so casually, so systemically dismissed? Following that dismissive echo, a different kind of echo began to form inside Joan Feynman, one of pure, unyielding resolve. She refused to be a footnote in her own life story. She earned her degree from Oberlin College and then set her sights on a doctorate, enrolling at Syracuse University in the 1950s. The world of postgraduate physics was, to put it mildly, not a welcoming one for women. It was a fortress of tweed jackets, pipe smoke, and impenetrable male camaraderie. Walking into the physics department was like entering a private club where she was not a member. We can picture her there, the lone woman in a lecture hall filled with men, the quiet determination on her face as she absorbed complex theories of quantum mechanics and electromagnetism, her presence a silent act of defiance. The air itself, thick with chalk dust and the low murmur of male voices dissecting equations, was a constant reminder of her otherness. This wasn't just a feeling, it was a statistical reality. According to data from the National Science Foundation, in 1958, the year she earned her PhD, women received fewer than 2% of all doctorates awarded in physics in the United States. She was an anomaly, and the system treated her as such. Her early papers, including her doctoral thesis on the absorption of infrared radiation, were technically brilliant, but it was her later work that set her on the collision course with the great cosmic mysteries. She pivoted to the nascent field of geophysics, focusing on the sun's influence on the Earth. This was the frontier. The term solar wind, a constant stream of charged particles flowing from the sun, had only been formally proposed by Eugene Parker in 1958. Joan was there at the very beginning, working to understand how this invisible celestial river interacted with our planet's magnetic shield, the magnetosphere. Her work involved painstakingly analyzing data from early satellites and ground-based magnetometers, searching for patterns in a chaotic storm of information. Her calculations mapped intricate plasma physics, translating the faint squiggles on a chart into a coherent story of cosmic forces. She was revealing, for the first time, the predictable rhythms hidden within the sun's seemingly random violence, linking specific solar phenomena to geomagnetic storms on Earth. This is where the systemic resistance became insidious. Her insights were undeniably valuable, but the credit was often diffuse. In the collaborative, hierarchical environment of mid-century scientific labs, it was tragically common for the contributions of junior scientists, and especially women, to be absorbed into the work of the lab director or senior male colleagues. Her name might appear on a publication, but often second, third, or fourth, a position that obscured her role as the primary intellectual driver. Her breakthroughs were relegated to footnotes, mentioned in passing, in the acknowledgments, or attributed broadly to the team or the lab. This academic sleight of hand is not just a matter of ego, it is a matter of career survival. Citations are the currency of science. Without a strong publication record as a lead author, securing funding, achieving tenure, and gaining access to better resources becomes nearly impossible. The scientific community, blinded by the ingrained gender bias that the high school professor had so crudely articulated, was slow to acknowledge the singular brilliance driving these breakthroughs. Her male counterparts, who may have been no more talented, saw their careers accelerate while hers was held in a state of perpetual potential. They were seen as pioneers, she was seen as a helper. This invisible labor, this theft of intellectual ownership, was the quiet, grinding injustice she faced daily. For years, she was the ghost in the machine, the architect whose name was left off the blueprint. How long could such pivotal work remain in the shadows? Building on those foundational insights, the sheer force of Joan Feynman's discoveries eventually became too significant to ignore. Her journey took her from the High-Altitude Observatory to the National Center for Atmospheric Research and, crucially, to NASA's Jet Propulsion Laboratory. At these elite institutions, the practical need for her expertise began to outweigh the ingrained prejudice. The space race was in full swing, and a new, urgent problem had emerged: protecting astronauts and billions of dollars of satellite technology from the sun's violent outbursts. The beautiful Aurora she had admired as a girl was the visible symptom of a much larger and potentially destructive phenomenon. It was here, amidst the harm of mainframe computers and the intense pressure of the Cold War, that her life's work culminated in a revolutionary breakthrough. She synthesized decades of her own research into a comprehensive model that finally cracked the Aurora's code. This was what some now refer to as the Feynman Diagram for Auroras. It was not a quantum diagram like her brother's famous creations, but a powerful conceptual and predictive model that connected the dots between the sun and the earth in a way no one had before. She demonstrated with overwhelming evidence that the most predictable and recurrent geomagnetic storms were not caused by dramatic explosive solar flares, as was commonly believed, but by something more subtle: the interaction of high-speed solar wind streams with the slow-speed wind. She identified the source of these streams and mapped how their collision sent shock waves rippling across the solar system. This model, documented in numerous peer-reviewed journals, including the prestigious, was a paradigm shift. It provided a method for predicting the arrival of these storms days in advance, a feat that had previously been impossible. Her model was tested against reams of satellite data from missions that were charting the space between the planets. The data confirmed it. Her predictions worked. Yet, even at this stage, her pioneering efforts were met with skepticism. The world of space physics was still a club, and her ideas challenged the established wisdom held by many of its most powerful members. At conferences, she would have to defend her work with a rigor and tenacity that her male colleagues were seldom required to muster. But data is a stubborn thing. As her model's predictive accuracy was proven time and again, the resistance began to crumble. The impact was monumental and immediate. Her work became the bedrock of modern space weather forecasting. Who benefited? We all did. The reliability of our global communications network, the accuracy of the GPS in our phones, the stability of our power grids, and the safety of astronauts in orbit all depend on the ability to anticipate these solar storms. When a coronal mass ejection hurtles toward Earth, it is Joan Feynman's foundational work that helps us prepare, allowing satellite operators to put their craft into safe mode and utility companies to protect transformers from catastrophic failure. The woman who was told she couldn't do math created the very mathematical models that act as a shield for our entire technological civilization. The reckoning is quiet but profound. Joan Feynman was eventually honored with the NASA Exceptional Achievement Medal and was elected a Fellow of the American Geophysical Union. But this recognition came late in a long career defined by a fight for the right to simply do the work. Her story forces us to look back at the system that tried to silence her and ask the unavoidable questions. Who benefited from the decades of delayed recognition? Whose careers were built on the foundations she laid, but for which she received little credit? And most importantly, what other celestial secrets might have been unlocked? What other global protections might have been developed sooner if her voice had been amplified from the very start? Her legacy is written not just in scientific journals, but in every satellite that safely navigates the void and every shimmering aurora, now understood not as a mystery, but as a testament to a mind that refused to be dismissed.